Welcome to lecture 13 of the course Statistical Thermodynamics for Engineers. So, as we saw already that the Bohr's model, while it was good, it felt a little ad hoc because it had part classical, part quantum mechanics in it. So, as we know that from standard electromagnetic theory, okay, that macroscopic radiation can be modeled successfully by a classical wave equation that we know, right? That from electromagnetic theory, that classical theory of waves, okay, predicts the macroscopic radiation. Okay. Now, shouldn't for atomic dimensions, okay, matter behaves like a wave. Matter behaves like a wave. Okay, matter behaves like a wave, and so shouldn't a similar wave formulation be applicable to the macroscopic behavior of matter? Hold for microscopic behavior of matter. Okay. So unlike this part classical, part quantum mechanics that we actually had from Bohr, can there be a more uniform framework which can be used in this particular context? So this actually set the stage for Erwin Schrodinger, Austrian physicist. He formulated what is called the wave equation. Now, this wave equation is now one of the cornerstone. The wave equation is one of the cornerstone of the fundamental law of quantum mechanics. Fundamental law of quantum mechanics. But we are not going to do a full derivation. We are going to have a heuristic understanding of the Schrodinger wave equation in general. Okay, so let us start to do that. For 1D electric field E, this is like the analogy. Electric field E is given as partial. For this is one dimensional. E square E by E square. D is basically nothing but a wave velocity. Alright. So this is from traditional electric field. This is well known. What Schrodinger did was that he defined wave function psi for matter waves, following de Broglie's great hypothesis. So he defined wave function for matter waves. Okay, so this wave function is nothing but this. E square. So this is a wave function, very similar to this. You can take an analogy and see what does it actually look like. Now, many solutions are possible for this particular equation, and have many solutions. Okay, but we consider the most well-known solution the most well-known solution. Okay, so that well-known solution is psi x comma t equal to c e to the power of I kx minus t. Okay, a is equal to 2 pi by lambda, omega is equal to 2 pi to the frequency. This is the frequency. Okay. This is like a propagation number. This is like a propagation number, so to say. Okay. So this is quite clear. So the wave velocity v that we have is equal to this gamma into lambda, which is basically we also have it as omega divided by this propagation number. Okay, so this is the solution. So once the solution is set, now we have to solve this equation. So you use the separation of variables. That means psi x comma t is equal to x of x into t of t. It's a well-known separation of variable. So this is substituted in the Schrodinger's wave equation. You get a double dot t is equal to 1 over v square x t double dot. Okay, so double dot signifies the second derivative. Or in other words, x double bar by x is equal to t double dot by t is equal to minus v square. Okay? Minus v square. Okay. So that is what it is. So now the total energy is T plus V. This is kinetic energy. This is potential energy. Okay. Now this can be represented as E squared by 2m plus V. The E is nothing but the linear momentum. Okay. For matter waves, A is equal to 2 pi E by h, which is P by h bar, where h bar is equal to h by 2 pi centimeters. Alright, so now that we have it, okay, so the first expression, if we look at it, is x double dot plus k square x is equal to 0. Or in other words, x double dot plus p squared by h bar square x is equal to 0. This is the first after the separation of variables. One is spatial and one is temporal. That's how we look at it. Or in other words, x double dot plus 2m E minus b, E being the total energy, divided by h bar square to x is equal to 0. Or, in other words, minus h bar square by 2m x double dot plus px is equal to px. Okay? Multiply by t, which is the temporal part. This becomes h double dot 2i into x double dot t plus vxt equal to ext. Okay? Or in other words, this actually becomes minus h bar square by 2m. Okay? square plus p psi, because this was actually a psi, is equal to epsilon psi. Okay. Now recall that the general solution was psi x comma t was c e to the power kx minus omega t. Okay. So d psi by dt is equal to c e to the power I kx minus omega t minus I omega, or I h bar psi by dt is equal to minus I omega I h bar c e to the power minus kx minus omega t. Okay? Or h bar d psi by dt is equal to omega h bar c e to the power I kx minus omega t, or I h bar d psi by dt equal to omega h bar psi x t. Okay, now E is equal to h nu, which is equal to h bar into omega. Therefore, I h bar d psi by dt is equal to t. Now, if you take this expression now, okay, and you take this all the way and apply it right here, okay, you take this, so let's call this 2, and if you call this 1, we take 2 and apply it to 1, okay, and substituting therefore, we get minus h bar square of 1 psi by x square or the p psi, okay, is equal to I h bar p psi by t. Alright? But in a more generic way, more generic fashion, what we can do with that, this will be minus h bar square h. This is the Laplace. Psi plus p psi is equal to I h. Okay. Now, if we define h hat, okay, h hat is defined as minus h bar by 2m, the Laplace plus v. Okay, so this particular operator is called an Hamiltonian operator. Okay. So therefore, once you cast it in terms of the Hamiltonian operator, is equal to I h bar d psi by dt. So this is the time dependent Schrodinger equation. Okay, so this is the time dependent Schrodinger's wave equation. Okay, let's see that if we have missed anything here. So it once again, it is a heuristic way of understanding the whole thing. So we have done a lot of math. Let us just do a very quick recap. So we had, at the atomic dimensions matter should behave like a wave. So therefore, similar wave formulation can be done for matter. So Schrodinger, by taking analogy from the one-dimensional electric field equation, Schrodinger defined the wave function for matter waves. And of course, this is the wave function, this is the wave equation. Many solutions were possible, but we take the most well-known solution, which is this. And then what we did what we call separation of variables. Okay, separation of variables, and this is the most common solution, as we say. So we did a separation of variable. So basically spatial and temporal. So this was the solution. This was the solution that we got over here. So that was the solution. Sorry, missed the V-square over there. So the total energy was taken as kinetic energy plus potential energy. So this is given in terms of the momentum. For matter waves, the K can be written like this in terms of the linear momentum. So then we went to the motion. Okay, we substituted this, and then we ultimately multiplied this by t, the time-dependent portion, and we got this expression. Right? Once we got that expression, we took the temporal derivative. Okay, and we showed that this is what it is. The temporal derivative is given as this. Now we took this temporal derivative now, and we substituted it here. Okay, we substituted it here because this was exactly the same as this. So this part is basically substituted. That's what we have done, and therefore we get this. And now then we say that this, let us consider this as the Hamiltonian operator. Okay, and this Hamiltonian operator therefore gives the final form of the equation, which is basically the time-dependent Schrodinger's wave equation. Okay. So this is a heuristic development, does not constitute a proof of the Schrodinger's wave equation, but instead a rationale for its formulation. Ultimately, its veracity depends solely on its utility, that how well it is able to address the atomic or the molecular dynamics. So at the same time, there is a nice, using de Broglie's platform. Okay, we have been able to get to this time-dependent Schrodinger's analysis. Now the problem that plugged this particular wave equation. Okay, so this wave equation was plugged by difficulties. Okay. Basically, the difficulties came in assigning okay, a practical meaning to the wave function. We could not assign a practical meaning to the wave function. It was like so like for example, if we say that this is the wave function, it can be xt, can be rt, say defining as the amplitude. If we say this is the amplitude of, say we say amplitude of matter waves. It's too vague a definition, right? Too vague a definition, and did not offer a clear link between model and experiment. No clear link between model and experiment. So that's too bad. There is no clear link between the model and experiment. So it offered really no real insight, and it was vague. There was no physical meaning to it. Okay, so what happened after that was that Max Born, the German physicist, ultimately provided a rationale to it. Okay, so he said he ultimately realized that if we multiply the wave function with its complex conjugate. Okay? It basically led to a definition of the probability density function. Led to a probability density function for particle behavior. Provided so itself it is not, it does not mean anything, but it provided a probability. So basically, if you multiply psi by its complex conjugate psi star, okay, this offers the probability density, PDF basically, PDF for particle. This is what Max Born. But itself, this offers no physical association with in known physical quantity. Okay, so that was the problem. That it did not provide with a physical rationale behind it. Okay, so the physical significance comes. Okay, the physical significance comes when the wave function is operated on by various mathematical operators. That's where the physical significance comes from. You understand? See, only the wave function which is operated by different mathematical operators, then only we get a physical significance associated with it. Okay? So the general procedures for identifying and assessing solutions to the Schrodinger's wave equation are delineated by basically 4 basic postulates. So we are going to deal with the postulates in the next class because there are a set of postulates. But postulate 1, you can easily see that basically psi star into psi, or the wave function multiplied its complex conjugate, is the probability. So that we already know. So that would be some kind of a first postulate. But you can see once a mathematical operator, when the wave function is associated with a mathematical operator, then only we get a physical significance of that particular quantity. So it's almost like a weightage fraction, some kind of a probability cloud, okay, for a particular variable, whatever that variable be it, and then only the physical significance arises, okay, for any dynamic variable. So whatever that dynamic variable can be, okay. So in this particular thing, what we have learned so far, before we go to the 4 postulates, is that de Broglie's hypothesis that matter waves should be present, because if light can behave like a particle, why not matter behave like a wave? Okay, so that set the stage, and he showed that for electrons, and we showed it by an example, that for an electron in that atomic dimensions, the matter waves are very important because they are almost of the same order as the radii. So that actually set the stage for Schrodinger to devise some more universal framework, so to say, so that all these things can be reconciled under one framework and not have this part mechanical, part classical approach as was done by Bohr's model, right? So there the wave mechanics took ideas from an electric field theory, and then it is applied for an arbitrary quantity which is called the wave function, the significance of which was done later on by Max Born, who said that, okay, this probably indicates a mathematical probability of a particle. Okay, and then once it is this is applied to different dynamic variables, position, momentum, etc., then it gives rise to the average position, average momentum of all these particles combined. So, and that can be now further used to calculate energies and other type of stuff. So we can see the progression. There was a historical perspective how the quantum mechanics evolved, because one had to identify those EJs and GJs, if you remember, for calculating, properties. So that was the first thing that we did. Okay, and so to get these EJs and GJs, we followed this very elaborate, understanding of quantum mechanics, because this can only come from quantum mechanics, this we have said again and again. So therefore, we started with Bohr. We showed how the classical model was inappropriate. So then we had the Max Planck, then how Bohr actually, how Einstein used it to show the duality, then de Broglie came into the picture, then how Bohr showed it was quantized, the orbits were quantized, the angular momentum was quantized, so the radius, the orbits at which the electrons will reside are also quantized. So this sets the stage that from an electromagnetic perspective, how the wave equation can be used now as a cornerstone of quantum mechanics. So in the next class, what we are going to do, we are going to advocate four postulates. These postulates are postulates of quantum mechanics, and then we are going to see how these postulates can be used subsequently to find out about the different dynamic variables and how it can be applied in quantum mechanics analysis that we will do in the next few classes. So thank you. So this is the end of lecture 13.